Hello dear students, welcome back to chemistry class. In our previous classes, we have covered one unit each from each of organic, inorganic as well as physical chemistry. So today, we will start another unit from physical chemistry, that is unit 4, chemical kinetics. Now chemical kinetics, it is the branch of chemistry that deals with rates of reactions and their mechanisms. So let us first try to understand what is rate of a reaction. Rate of a reaction simply means the speed of the reaction. That means if the reaction takes place in a very fast way, the rate will be high. If it takes place slowly, the rate will be low. Rate, it is defined as the change in concentration of either of the reactants or products per unit time. Now, in physics, we determine the speed of a vehicle by dividing the distance covered by the time taken. Distance covered by time taken gives us the speed of a vehicle. Likewise, for a chemical reaction also, the speed can be calculated by dividing the change in concentration of any one of the reactants or products by the time taken. So, for example, if a reaction takes place and the reactant A turns into product B. Suppose for A to turn into product B, 5 seconds is required when 10 moles of A is consumed. Suppose we start with 100 moles of A. In 5 seconds, if 10 moles of A is consumed, and suppose 5 moles of P is produced, then we can use the change in concentration of any one of this, either the reactant or product, to calculate the rate of the reaction. So rate will be given by change in concentration of the reactant divided by time, or it can be also given by change in concentration of the product divided by time. In the case of the reactant, it is consumed during the course of the reaction. So if we start with 100 gram of A, and in 5 seconds, if 10 gram of A is consumed, then the change in concentration of A will be 10 gram. The time taken will be 5 seconds. This change in concentration of the reactant divided by the change in time will give us the rate of the reaction. Similarly, in the case of products, it increases. We start with 0 gram of the product. In the beginning, there will be no products, but once the reaction starts and it goes on, then the reactant starts forming. The product starts forming, and the concentration of the product will go on increasing in the course of the reaction. So the increase in concentration of the product divided by the time taken will also give us the rate of the reaction. So here, rate can be defined as the change in concentration of either the reactants or products per unit time. But one thing to remember, in the case of rate, when defined with respect to concentration of the reactants, we use a negative sign here in this equation. This negative sign indicates that the concentration of the reactant goes on decreasing. But for the product, it will be positive. So change in concentration of the product divided by time, this will be positive. This to indicate that it goes on increasing in the course of the reaction. Now the relations that we just derived, these are called as average rates of reactions. Average rate of a reaction, it can be defined as the rate of change in concentration of either the reactants or product in a given measurable period of time, or in a specified measurable period of time. So once again, let me write a reaction in which R, the reactant, turns into product P. The average rate can be represented like this. Average rate of the reaction will be equal to the change in concentration of the reactant by change in time. Remember, this sign tilde indicates change. So change in concentration of reactant divided by change in time. But as mentioned before, if we are writing the rate in terms of concentration of the reactants, this will be negative. For the product, it will remain positive. So tilde P divided by tilde T will give us the rate of the reaction. This gives us the average rate of the reaction. Let us see an example here. If concentration of a reactant A changes from 0.055 mole per liter to 0.028 mole per liter in 32 minutes. What is the average rate of this reaction? To calculate the rate, average rate will be given by the change in concentration of reactant by change in time with a negative sign, or change in concentration of product divided by change in time. Any of these two we can use to calculate the average rate. Now here in the question, concentration of reactant A changes from 0.055 to 0.028. The change in concentration of reactant is given, so we will use this relation. Rate will be equal to negative of tilde R divided by tilde T. Now, change in concentration of the reactant, it changes from 0.055 to 0.028. So this gives us 0.027. The time taken, the change in time, is 32 minutes. Concentration is given in mole per liter. Time is given in minute. So 0.027 divided by 32 should give us 0.000844 mole per liter, and minute, if we bring it up, it will come out as per minute. This, if we write in standard form, it will become 8.4 into 10 to the power 1, 2, 3, 4. It moves 4 places to the right side, so this becomes 10 to the power minus 4 mole per liter per minute. This is how we can calculate the average rate of the reaction. Now, in order to understand the mechanism of a reaction properly, we need to know the rate of the reaction at a particular instant of time. We cannot use this average rate to calculate the rate at a particular instant of time, because for that given time, the average rate will remain constant. So we have another rate which is called as the instantaneous rate. This is the rate, that means the change in concentration of reactant or product at a particular instant of time. Now this instantaneous rate can be obtained when we consider the average rate at a very small change in time, or when tilde t, the change in time, approaches 0. So for writing the instantaneous rate, instead of tilde, we use the sign del. This will indicate a very small change in concentration of the reactant by a very small change in time. So when we consider the average rate at the smallest time interval possible, That means when delta T approaches 0, and which is represented by this sign till, we get the instantaneous rate. So instantaneous rate for the reaction will be change in concentration of reactant by change in time when delta T approaches 0. Or it can be change in concentration of the product also divided by change in time. Now, if we consider a reaction in which the stoichiometric coefficients of reactants in products are the same, let us see an example. If we have a reaction in which mercury reacts with chlorine gas to give mercury chloride. In this reaction, 1 mole of mercury combines with 1 mole of chlorine to give this mercury chloride. Here, it's not written here, but this shows that 1 mole of mercury combines with 1 mole of chlorine, and 1 mole of this product is formed. So the stoichiometric coefficients are the same, 1 each. In this kind of reactions, the rate, whether it's average rate or instantaneous rate, it will be the same like the equations that we wrote before. Rate will be given by change in concentration of any one of these products. So we can use mercury also, or we can use the change in concentration of chlorine also, or we can use the change in concentration of the products. Any one of these can be used to calculate the average or instantaneous rate of the reaction. Now here, from this we understand that the rate of disappearance of mercury, or the rate at which mercury is consumed, is equal to the rate at which chlorine is also consumed, and that is also equal to the rate at which this product mercury chloride is formed. So we can just represent the rate of the reaction like this. But if we have another example in which these stoichiometric coefficients are not the same, let's take the case of decomposition of hydrogen iodide to give hydrogen gas and iodine gas. In this one, 2 moles of iodine gives 1 mole of hydrogen and 1 mole of iodine. So here, the stoichiometric coefficients are not the same. Here we have 2, here we have 1 each. This means that the rate at which hydrogen iodide is consumed is not equal to the rate at which these two products are formed. In other words, the rate at which hydrogen iodide disappears is 2 times the rate at which hydrogen and iodine are formed is equal to 2 times the rate at which hydrogen iodide is consumed. So since the stoichiometric coefficients are not the same here, and since the rate of disappearance of the reactant is not equal to the rate at which the products appear, we have to divide these equations by the stoichiometric coefficients. Let us try to understand it like this. Rate of the reaction will be equal to the change in concentration of hydrogen iodide divided by change in time. This will be divided by the stoichiometric coefficient, that is 2. So we write 1 by 2 here. Here, number of moles is 1 only. So change in concentration of hydrogen divided by change in time will not be divided. or it will be divided by 1 only. Here also, change in concentration of iodine by change in time will be divided by 1 only. By dividing the change in concentration by the stoichiometric coefficient, we make this equal now. So whenever we have reactions like this, where the stoichiometric coefficients are not the same, we have to divide the equations that we wrote before with the stoichiometric coefficients that are used in the balanced chemical equations. Now for gaseous reactants, when the temperature is constant, concentration is directly proportional to the partial pressure of a species, and hence rate can be expressed as rate of change in partial pressure of the reactants or product. So if we have a reaction in which a gas reacts with another gas, suppose nitrogen and hydrogen, both of them are gases, they react to form ammonia, which is also a gas. In these gaseous reactions, if the temperature is kept constant, then the rate can also be expressed in terms of in terms of change in concentration of pressures. So rate or the average rate will be equal to the change in partial pressure of nitrogen by change in time. Instead of change in concentration, we can use the change in partial pressures. Likewise, for hydrogen also, we can use the change in pressure of hydrogen. And for ammonia also, it will be the change in pressure of ammonia divided by time. So whenever gaseous reaction takes place under constant temperature conditions, we can use either the change in concentration or the change in pressure of the reactants or products to calculate the average rate of the reaction. Let us quickly see another reaction here. An example. In a reaction where 2 moles of a reactant A turns to products, the concentration of A decreases from 0.5 mole per liter to 0.4 mole per liter in 10 minutes. Calculate the rate. During this time. Here, 2 moles of A gives 1 mole of the product. That is what we understand from this given equation. So rate will be equal to the change in concentration of A divided by time. Since 2 moles of A gives only 1 mole of the product, then this equation will be divided by 2. So change in concentration of A will be 0.5 minus 0.4, that is 0.1 divided by the change in time, that is 10 minutes. So we get 0.1 divided by 2, or 1 divided by 200. This will be in moles per liter per minute. That is all for today. We will continue with the same topic in the next class. Thank you.